Consider one example on designing of lattice structure. Determine the lattice coefficients corresponding to the FIR filter with system function h of z and sketch the lattice structure. That is, in this case, suppose this is a system having transfer function, say a3 of z. Let x of n is the input and say y of n is the output. In this case, the output sequence or output signal y of n is given by x of n plus summation k equal to 1 to m alpha m of k x of n minus k. This is the standard form. We'll call it as equation 1. So in this case, m is equal to 3. That is, given m is equal to 3. Therefore, now equation 1 can be expanded as y of n is equal to x of n plus summation k equal to 1 to 3 alpha m of k x of n minus k. Expanding this summation, I can write x of n plus, for k equal to 1 and m equal to 3, I can write it as alpha 3 of 1 x of n minus 1, as I have taken k equal to 1, plus, now for k equal to 2, here m value is 3, I can write it as alpha 3 of 2 x of n minus 2, plus for k equal to 3, it will be alpha 3 of 3 x of n minus 3. We'll call it as equation 2. That is y of n. So now I will concentrate on h of z, given h of z. So here given h of z can be represented as h of z is equal to, I can write it as y of z divided by x of z, which is equal to 1 plus 13 by 24 z inverse plus 5 by 8 z power minus 2 plus 1 by 3 z power minus 3. Further, I can simplify this as, I will send this x of z on other side. Therefore, I can write y of z is equal to, I'll multiply this x of z with each term of this, so that I can get x of z into 1 plus 13 by 24. We have z inverse into x of z plus 5 by 8 z power minus 2 x of z plus 1 by 3 z power minus 3 x of z. So now we'll take inverse z transform of y of z. That is, I can write taking inverse z transform. I will write here the inverse z transform of y of z is y of n is equal to inverse z transform of x of z is x of n plus 13 by 24. Inverse z transform of this is x of n minus 1 plus 5 by 8. Inverse z transform of z power minus 2 x of z is x of n minus 2 plus inverse z transform of this is 1 by 3 x of n minus 3. So now we can compare equation 2 with equation 3. We can write compare equation 2 and 3. So here we can write alpha 3 of 1 is nothing but 13 by 24. That is, alpha 3 of 1 is equal to 13/24. Similarly, the coefficient of x of n minus 2 is alpha 3 of 2. Here coefficient of x of n minus 2 is 5/8. Alpha 3 of 2 is 5/8. Similarly, coefficient of x of n minus 3 is alpha 3 of 3, which is nothing but 1/3. So here alpha 3 of 1, alpha 3 of 2 and alpha 3 of 3 are known as direct coefficients. These are direct coefficients. So now we supposed to find, to get the lattice structure, we supposed to find lattice coefficients. Now we need to calculate lattice coefficients K1, K2 and K3. So here m is equal to 3. So we supposed to calculate the coefficients till 3, that is K1, K2 and K3, because m is equal to 3. So now let's see how to convert the direct coefficients into lattice coefficients K1, K2 and K3. We know that Km is equal to alpha m of m, alpha m minus 1 of 0 is equal to 1, alpha m minus 1 of k is equal to alpha m of k minus alpha m of m into alpha m of m minus k whole divided by 1 minus alpha m of m whole square. So we'll call it as equation A, say this as equation B and this as equation C. So these three equations are used to convert direct coefficients into lattice coefficients. So one should remember these three equations to get the lattice structure from the direct coefficients. From A I can write, if I take m equal to 1, I can write K1 is equal to alpha 1 of 1. Similarly, if I take m equal to 2, that is K2 will be equal to alpha 2 of 2. And if I take m equal to 3, K3 will be equal to alpha 3 of 3. So here we can see that alpha 3 of 3 value is already obtained, that is 1/3. So its value is equal to 1/3. So already we found K3. Now the task is to calculate K1 and K2. So now finding K1 is nothing but alpha 1 of 1. So we'll try to calculate alpha 1 of 1 using equation C. So in equation C, if we consider m is equal to 2 and k is equal to 1, we'll get alpha 1 of 1. Therefore, if m is equal to 2 and k is equal to 1, then equation C can be written as, that is, now I'll write this equation for m equal to 2 and k equal to 1, that is alpha 1 of 1 is equal to, we are taking m is equal to 2, that is alpha 2 of 1 minus alpha 2 of, here we have m 2 of 2 into alpha m is 2 alpha 2 of 2 minus 1 is 1 whole divided by 1 minus alpha m of m, that is alpha 2 of 2 whole square. We'll call it as equation 1. So now in equation 1, to get alpha 1 of 1, we should know the value of alpha 2 of 1. So here you can find alpha 3 of 1, alpha 3 of 2, alpha 3 of t. But here alpha 2 of 1 is value is not available. Alpha 2 of 2 value is not available. As well alpha 2 of 1 value is not available. So now again we'll try to find alpha 2 of 2 using the same formula, that is C, by taking m equal to 3 and k equal to 2, so that we can get alpha 2 of 2 variable. Let m is equal to 3, k is equal to 2. Equation C can be written as alpha 3 of 3 whole square. I can write, so alpha 3 of 2 value is, here we have alpha 3 of 2, that is 5 by 8, minus alpha 3 of 3 value is 1 by 3, into alpha 3 of 1 value is 13 by 24, divided by 1 minus alpha 3 of 3 whole square. Alpha 3 of 3 is 1 by 3 whole square. So here this alpha 3 of 3 can sometime also be represented like this, alpha 3 of 3 square, which is same as alpha 3 of 3 square. One should remember this. So therefore simplifying this, I can write alpha 2 of 2 is equal to, so this will get 4 by 9 divided by 8 by 9, which is equal to 0.5. So therefore alpha 2 of 2 is equal to 0.5, which is nothing but 1 by 2. So in this equation we found alpha 2 of 2, but alpha 2 of 1 is value is not available. Alpha 2 of 1 value can be evaluated by taking m is equal to 3 and k is equal to 1. Therefore let m is equal to 3 and k is equal to 1. Equation C can be written as alpha 2 of 1 is equal to, this is alpha 3 of 1 minus, this is alpha 3 of 3 into alpha 3 of 2 divided by 1 minus alpha 3 of 3 square. So simplifying this, we know alpha 3 of 1 value, that is 13 by 24. 13 by 24 minus alpha 3 of 3 value is 1 by 3 into alpha 3 of 2 value is 5 by 8 divided by 1 minus alpha 3 value is 1 by 3 square. So simplifying this, whole divided by 8 by 9, simplifying this will get 3 by 8. Now we'll try to find alpha 1 of 1, that is equation number 1. Therefore from equation 1, alpha 1 of 1 is equal to, we have alpha 2 of 1 alpha 2 of one value is 3 by 8 minus alpha 2 of 2 value is 1 by 2 or 0.5 into alpha 2 of 1 value is 3 by 8 whole divided by, we have 1 minus alpha 2 of 2 square. 1 minus alpha 2 of 2 is 0.5 square. So simplifying this, we'll get 0.25. So alpha 1 of 1 is nothing but k1. So therefore I can write alpha 1 of 1 is nothing but k1, which is equal to 1 by 4, that is 0.25. Similarly, alpha 2 of 2 is nothing but k2, its value is 0.5, and alpha 3 of 3 is nothing but k3 and its value is 1 by 3. This is 1 by 2. So now for understanding purpose, here I will draw direct form structure, how it looks like. This is the direct form structure. Here I can write direct form structure is shown below. Here m, for m is equal to 3. So here I can write alpha 3 of 1 value is, alpha 3 of 2 value is, and alpha 3 of 3 value is 1 by 3. Now the corresponding lattice structure I will draw here. The lattice structure is shown below for m is equal to 3. So this is the lattice structure. Here we have the input x of n. This is plus, this is plus. Here we have z inverse, and this is nothing but k1. Its value is 0.25, that is 0.25. This is k2. Its value is 0.5. This is plus, this is plus. This will be z power minus 2. This will be z power minus 3. This is plus, this is plus. Here we have k3 and its value is 1 by 3. So here will be the output y of n. So this is the lattice structure which is required, where we have found k1, k2 and k3. Here this is also k1 only. This is k2, right here k1, k2, and this is k3. This is corresponding lattice structure for the given direct form structure. Thank you for watching.